In this video, we will look at how these atoms are arranged in metals. So far we have discussed about the different types of crystals and Bravais lattices. Now, the first important thing we need to understand that in metals, in metals, you have metallic bonds. See, these metallic bonds are non-directional. So it is non-directional. So this is a fact. So this will form bonds, try to form bonds in uh, all directions. And second important thing you need to keep in mind is that uh, atoms form as many bonds as possible. Bonds as possible because forming more bonds reduce the energy of the system. So it will try to form as many bonds as possible. So that is also a fact that we need to keep in mind. Then, in order to visualize the structure of solids, we assume these atoms as hard spheres. So this is partly true. You can assume the atoms to be hard spheres, and you can assume this to be non-overlapping hard spheres. Okay. So the atoms are arranged in a crystal like the hard spheres, which are non-overlapping with each other. So this is one point you need to keep in mind. So based on these ideas, we will try to visualize the structure of metals. And another point also we need to keep in mind is that, for example, in a metal or in element, these all atoms are identical. All atoms are identical. So you can assume this to be equal hard spheres. So based upon this, we will look at the idea of close packing of hard spheres. So this is how you're going to visualize the structure of metals. Okay. So let us first take the so how these atoms are packed. So first let us take the one-dimensional packing. So that means you can assume these atoms to be hard spheres. So here let us as you can consider only in one dimension. So these atoms are lined, are li- lined like this. Okay, so this is the total length. Okay, so if it is one dimensional, you can assume these hard atoms just which are non-overlapping, that is just they are touching each other. That is exactly they, we can assume this as hard spheres. So its packing efficiency, PE, or this is defined as the packing efficiency here, that is the total occupied length by the total length. So here total occupied length is L, so total length is also length. So here the packing efficiency is 100%. So this is how you find the packing efficiency for one-dimensional packing. Now let us look the case of 2D packing. Okay. So how the 2D packing is different. For that, uh, so let us assume the atoms are placed like this. So you can see that we are placing here an atom here. There is one line of atoms. So here also you can see that there is one line of atoms. There are two ways of arranging atoms. You can see that there is another plane of atoms on top of this, and another plane of atoms on top of this, and another plane of like this. And but in this case, you can see that this is an hexagonal layer because one plane of atoms is placed here. So another plane is placed like this. So another plane is placed like this, and another plane is placed like this. So this one is much more closely packed than this one. It is easy to find the packing efficiency of this hexagonal layer that comes out to be the packing efficiency here comes out to be 0.92 or 92%. We can derive it, but we are not deriving it at this moment. So this is how these atoms can be arranged. So hexagonal. So we will go for an arrangement which will give you the closest packing because the atoms will form bond as many bonds as possible. So we will only so atoms will be arranged in such a fashion that we have a closely packed structure. So we will so the hexagonal layer is the uh, type of packing we choose. But in reality, we have a 3D structure. Okay, so what happens in a 3D structure? Let us look that in detail. Okay, so here you can see that we have seen already how the atoms are packed in 2D. We have seen the hexagonal layer of packing, and if you pay attention, you can see that for 3D packing, first we will have a 2D packing. First, we will have a one-dimensional packing, and then you will have a two-dimensional packing, on top of which we will add the another layers. So here you can see that. So this is a 2D packing we have seen earlier. This is a hexagonal packing. And you can see that there are points like this. So I have marked points A. So this is the center of atoms here. These are the center of atoms. Okay. So you can place atoms on top of this. Okay, on top of this. But how do you place the atoms? So where will the next layer of atom will go? So if you look carefully, so I will draw a triangle. Here I will draw a triangle, and here also I will draw a triangle. So at this center, I will mark it as B, and here I will mark it as C. Okay, so here it will be B, here it will be B, here it will be B, here it will be C, C, C. On careful examination, you can see that if I place atom here, so if I place atom here, that is in the B position, I will not be able to place atoms on C. So the next layer can either go to B or C. It cannot be placed on B and C alone. So we will look at a different picture. This picture shows that you can see that if there is an atom on C, you cannot place atom on B. Okay, that is evident. Okay, so it will overlap each other. We have discussed we have seen that the atoms will never overlap each other. They will just touch like hard spheres. So if you look at this picture, I have placed atoms at the B position throughout. So the C portion is kept blank. Okay, so I have chosen the B position. So the first layer will occupy the A position, second layer will occupy the B position, and where will the third layer go? You can see that the third layer can go. So for close packing, it can either go to A or C. Okay, there is two options. So I can place an atom here. I cannot place an atoms on A and C. Okay, I can place atoms either on A or C. So that means so next layer can be A or C. Okay, based on this, you can see that. So how these layers are placed. So you have several positions like A, B, C, etc. Based upon how these layers are placed at various positions, you will get a different stacking sequence. So that is called the stacking sequence. You will get different structures, okay, different crystal structures. So these are the possibilities. That means first I can go to A, then B, then C, then A, B, C, like that. Or I can go in a different way. So B, A, B, then I can go A, B. So like that. Then again A, B, like that. Then, or I can go a different way, like see, it is A, C. Uh, then I can go like this, A, C, B, A, C, B, like that. So this A, this is not allowed because this is not closely packed. Okay? You need to keep that in mind. And this B, okay, this is also not allowed, and also C is not allowed because that is not closely packed structure. So the atoms will arrange themselves in a very closely packed structure. So these are the different stacking sequences. And the two important stacking sequence we need to keep in mind or study is AB, AB stacking sequence, and then you have or ABC stacking sequence. Okay, so the first one is called the HCP or hexagonally close pack structure, and this will lead to FCC, or you can this is face centered cubic crystal. Phase-centered cubic crystal. So we have studied about these lattices in crystals and Bravais lattices. So we will study about this stacking sequence in detail. So once more, this is called the stacking sequence. Stacking sequence.